I hope you're all doing well. On this channel, I share videos that highlight the importance of mathematical modeling techniques. I am currently explaining the Collatz operations introduced in this study. In this video, I will show how much the calculated value changes, that is, the rate of change, when each Collatz operation is applied to. To prove the validity of the Collatz conjecture, it is important to confirm that the calculated values eventually decrease 1. To do this, we need to clarify how much the calculated value changes when each Collatz operation is performed. Let us begin by considering a high-quality odd number A. Its general form is given by the following expression. As you may recall, high-quality odd numbers include the good quality odd numbers, a prime, and the better quality odd numbers, a double prime. When either of these appears during the iterative calculation process, we use its value in I and apply Collatz operation a prime or Collatz operation a double prime. The flow of calculation in this case proceeds as follows. The resulting value, in I plus 3, is either odd or even. If it is odd, it becomes either a high-quality odd number, A, or a low-quality odd number, B. Using Ni, the value in I plus 3 can be expressed as follows. Therefore, the difference between the final value and the initial value is given by the next expression. Substituting equation 1 into equation 3 gives the following result. Since j is a positive integer, ni plus 3 is always smaller than ni. The rate of change in I plus 3 divided by ni varies depending on the value of ni. Therefore, the rate of change can be expressed as follows. According to this expression, as the natural number ni increases, the value in I plus 3 approaches 75% of ni. When we assume that all natural numbers are used as initial values, it is convenient to use a single number to represent the slightly different rates of change. According to equation 5, the rate of change is 0.80 when p equals 5. It decreases rapidly as p increases, and it becomes 0.7525 when p equals 100. In addition, the description in the Zenodo paper that says 0.833 when p equals 3 is incorrect. The correct value is 0.80 when p equals 5. When all natural numbers are considered, almost all initial values become overwhelmingly larger than 100. Therefore, in this study, we represent the rate of change for Collatz operation A by a constant value of 0.75. Naturally, when this value is fixed, a calculation error appears in the iterative calculation, and the final calculated value becomes slightly smaller than 1 when the calculation reaches 1. Next, let us consider a low-quality odd number, b. Its general form is given by the following expression. When a low-quality odd number, b, appears during the iterative calculation and is used as the initial value in I, the flow of calculation for Collatz operation b proceeds as follows. The value given by this calculation, in I plus 2, becomes either a high-quality odd number, A, or another low-quality odd number, B. In this case, in I plus 2 can be expressed in terms of Ni as follows. The difference between the final value and the initial value is given by the next expression. Here, when we substitute equation 1 into equation 9 and replace Ni with Nj, we obtain the following result. Since j is a positive integer, Ni plus 2 is always larger than Ni. The rate of change, Ni plus 2 divided by Ni, takes different values depending on the value of Ni. This is expressed by the following equation. From this equation, we see that the rate of change becomes smaller as p becomes larger, and that it approaches a value of about 1.5 when p is sufficiently large. For the same reason as stated above, the rate of change for Collatz operation B is fixed at a constant value of 1.5 in this study. For even numbers C, the rate of change for Collatz operation C is 0.5, and this value is used consistently throughout the study. As described above, this study fixes the rates of change for Collatz operations a prime, a double prime, B, and C at 0.75, 0.75, 1.5, and 0.5, respectively, for the purpose of simplification. The changes in the iterative calculated values when n0 equals 27 are shown in the table. 53 Collatz operation types can be assigned to these values. When we perform the calculation using the rates of change mentioned earlier, the final calculated value becomes 0.834. In addition, the changes in the iterative calculated values when n0 equals 1 trillion, 10 billion, 101 million, 10,000, 101 are shown in the table. 123 Collatz operation types can be assigned to these values. When we perform the calculation using the rates of change mentioned earlier, the final calculated value becomes 0.798. These final values should, in principle, all be equal to 1, as shown in the table. However, they do not become 1 because the rate of change for Collatz operations a prime and a double prime was approximated as 0.75, and the rate of change for Collatz operation B was approximated as 1.5 when performing the calculation. For mathematicians, introducing such approximations into a proof is almost considered taboo. However, as I will show in a later video, using these approximations greatly simplifies the transformation of the equations. In addition, the original purpose of introducing the Collatz operations is to check how the calculated values change. As the previous examples show, the final calculated values obtained from the approximate calculation become close to 1, and this does not cause any problem when evaluating the validity of the proof. Furthermore, if we perform the iterative calculation using the exact values without any approximation, the final calculated value becomes exactly 1. This clearly shows that the values produced in the iterative calculation of the Collatz conjecture change within the framework of the 4 types of Collatz operations. That concludes today's talk. I look forward to seeing you again in the next video. Until then, take care.